Hello there. Welcome to AP Calculus, Lecture 2.5a. This is Introduction to Implicit Differentiation. So for this lecture, I've got a little note, pre-printed notes for you, and so we'll just go through this. And if you have a highlighter, it might help. But just going through the first bullet and on down the page, the definition of the derivative empowers you to take derivatives of functions, not relations. We're going to fix that today. So in this space here, let's just draw an x and y axis. And just draw a circle. So a circle fails the vertical line test, right? It's pierced if you take a vertical line and go from left to right. It pierces that curve in two places. So a circle is not a function. Fails the vertical line test, not a function. Right. The definition of the derivative, though, what we learned in the early part of Chapter 2, only allows you to take derivatives of functions. So for any particular x value, you'll get more than one y value, so that makes it a relation. However, we still might need to know the slope of the tangent line on any point on this circle. Maybe we want to know it there, or there, or there, right? So how do we get that? Well, a technique called implicit differentiation allows us to find the slope of the tangent line for relations. So Leibniz notation, we've seen that before. dy dx is that's the way that you say that is the derivative of y with respect to x. The derivative of y with respect to x. dy dx, you want to think of that as a noun. It's a thing. So right here, if we have y is equal to 3x squared minus 4x plus 1, then dy dx, we've done this many times. 2 times 3, we're just going to use the power rule, right? 2 times 3, 6. Subtract 1 from the exponent, minus 4. But the thing is, we actually skipped a step there. All right, we didn't really teach you that part, but we skipped the intermediate step. And to understand implicit differentiation, we need to introduce that intermediate step. So d dx, before I move this aside, d dx is a verb. And it means take the derivative of y with respect to x. So take the derivative of y with respect to x. So if we have the next bullet, this notation, (3x squared minus 4x plus 1), if we see that, that means we're actually supposed to take the derivative of both sides. So we're taking the derivative of y, and then we're taking the derivative of the right side, with respect to x, of both the left side and the right side. The derivative of y with respect to x is dy dx. Memorize that. The derivative of y with respect to x is dy dx. And then if the derivative of this function with respect to x is 6x minus 4. Everything we've always done, or at least since the beginning of chapter 2. Okay, so the example at the bottom of the page, and then we'll do some more significant examples. Let's take a look at that. It says differentiate y is equal to x squared. So this time I'm gonna do it with this intermediate step involved. I'm going to differentiate, take the derivative of this whole function with respect to x. All right, now I'm doing this the long way. We won't do it this way every time. We're taking the derivative with respect to x of y and the derivative with respect to x of x squared. All right, so this is dy dx. The derivative of y with respect to x, just y by itself, is dy dx. And that's 2x. All right, so we never used the fact that y equals x squared is a function. When we did the intermediate step of taking the derivative of y in addition to x squared, then that works for relations as well. All right. So now let's go into some more, fancier examples so that you can do the homework. Because a relation, you'll have all the x's and y's mixed up together. So our first example is find dy dx given x squared plus y squared is equal to 1. So you don't have to remember this, but you do need to recognize that this is a relation. In fact, it's a circle of radius 1. All right, circle of radius 1. So what I want to do is take the derivative with respect to x of x squared plus y squared is equal to 1. Okay, so I'm not going to do this every time, but maybe the first couple of examples I will. We're going to separate each element. We're going to take the derivative of x squared plus the derivative with respect to x of y squared. Okay, so I want to rewrite this like it's a chain rule. So we're going to take the derivative of, because this is easy and this is easy, with respect to x, let's rewrite it like this, as y squared. It's the same thing, but it helps me figure out what the derivative of that is. Okay, so moving down here, the derivative with respect to x of x squared is 2x. Okay, so this is a chain rule. You're going to bring the 2 out front and drop it to the first power. So it's going to be plus, so we're right here, 2 times y to the first, but I'm not going to write it. And then, so the outer function, write this in, the outer function is y squared. The inner function, which I'll put in red, is just y. So we've got the outer function, it's 2y, that times the derivative of the inner function. Well, what's the derivative of y with respect to x? It's dy dx. And then the derivative of a constant is 0. Now we're trying to solve for dy dx, so we want to have all the dy dx terms on one side. We'll put them on the left. And let's move this 2x over to the right. So we make it negative and move it to the right. And now we're going to solve for dy dx. We divide both sides by 2y. So bring that 2y underneath. We have minus 2x over 2y. The 2's will cancel. And the answer is negative x over y. So anywhere on that circle, if you put a point on the circle into negative x over y, it'll give you the slope of the tangent line at that point. So if we put this point in, it would give us a slope of whatever that is, whatever that point is we put in. All right, if we put this point in right here at the top, if we put in the point 0, 1, it would give us a slope of 0. The x value is 0, the y value is 1, 0 over 1. It'd give you a slope of 0. So it works everywhere on that circle. All right, let's keep going. We'll keep upping the difficulty of the examples every time. So our next example is we want to find dy dx for x squared plus xy plus y squared equals 10. All right, so we've got the x's and y's all mixed up here, so we can't take the derivative the old-fashioned way. That's not a function, it's a relation. So I'm going to invoke our verb, take the derivative of both sides, x squared plus xy plus y squared is equal to 10. So you're taking the derivative, this is the way we write it, of each component in this relation. Okay, so for x squared, that's easy. It's just 2x, right? But this is a product rule. The first times the derivative of the second plus the second times the derivative of the first. Okay, so the first is x. What's the derivative of y with respect to x? It's dy dx. So the first times the derivative of the second plus the second, which is y, times the derivative of the first, which the derivative of x is just 1. So I'm not going to write the 1. Now y squared, we just did that one, right? It's, if we write it, if we think of it like this, then the outer function is y squared, the inner function is y. So that'd be plus 2y dy dx. Outer function, the derivative is 2y. The inner function, the derivative is dy dx, is equal to 0. Now we have two dy dx terms. Let's keep these over on the left side. And we're going to shove the 2x and the y over on the right. So we'd have to make them negative. So minus 2x minus y. Now, we just want to solve for dy dx, so let's factor out a dy dx. If we do that, what we have left is x plus 2y. Right? Distribute that dy dx, and you come up with this. So we factored it so that we could now pull that x plus 2y underneath, solving for dy dx. So I've got negative 2x minus y over x plus 2y. And that is the derivative of this relation with respect to x. And at any point on this on the graph of this, if you plug in the x and y value, it'll give you the slope of the tangent line at that point. All right, pretty cool. Okay, let's do one even a little more fancy. One where we have to invoke the quotient rule. All right, let's find dy dx for x plus x over y minus y cubed is equal to 20. It won't always be a constant on the right side. I don't know why I keep doing that. So what we have to do is to use our verb, our action. We're going to take the derivative with respect to x of this entire thing. X plus x over y minus y cubed equals 20. Okay, what's the derivative of x with respect to x? It's not 0, by the way. I've had so many students do that. It's 1. Now we have a quotient rule. The bottom, y, times the derivative of the top, that's 1, minus the top, x, times the derivative of y with respect to x, that's dy dx, all over the bottom, squared. Okay, now we're at the y cubed term. So minus y cubed, think of it like this. So it's going to be 3y squared, so minus 3y squared, but don't stop there. That's the most common mistake in implicit differentiation, forgetting to take the derivative now of the inner function, which is y. So that's times dy dx. And that'll equal 0. Now this thing is a bit, that y squared on bottom is a real pain in the caboose. So let's eliminate it by multiplying both sides by y squared. This is certainly something we did in pre-cal a lot, or algebra 2. Now you wouldn't have had to written all this again. I'm just doing that for illustrative purposes. You could have just written the y squared up here and put brackets around it. So y squared times 1 is y squared. Y squared, and then we have a y squared on bottom. That eliminates the fraction. So we'd have plus y minus x dy dx. Y squared times 3y squared would be 3y to the 4th dy dx equals 0. Now let's gather all the dy dx's on the left. So I have negative x dy dx minus 3y to the 4th dy dx is equal to negative y squared minus y. Let's factor out a dy dx. I have negative x minus 3y to the 4th equals negative y squared minus y. Now I'm going to bring this negative x minus 3y to the 4th underneath. So dy dx is equal to negative x minus 3y to the 4th over negative y squared minus y. All right. So something appears a little wrong here. Oh, yeah, my bad. Reversed it here. So we would have negative y squared. Sorry about that. Negative y squared minus y over negative x minus 3y to the 4th. Okay, so bring this underneath here. Okay, so the back of the book, what the back of the book will do, this is the right answer. And on a test, I don't care if you leave it like this, but you're going to want to get it like the back of the book so you're not confused. they would factor a negative out of both terms. So y squared plus y, and a negative there, x plus 3y to the fourth, because they just want to get rid of all the minuses if they can, and then the negatives will cancel. So the back of the book will say y squared plus y over x plus 3y to the fourth. And I guess that does look prettier. Okay, but I'm totally fine with this as the answer as well. Okay, that's enough new material for today. Let's talk about the homework. So the homework is, let's see, what page are we on here? We're on page 139. And I'd like you to do 1, 3, 5, 7, 8, and 9. And let me give you a hint for number 8. And you don't have to use this hint, but you might find this helpful. If you have the square root of x times y, that's the same thing as x to the 1/2 times y to the 1/2. All right, so you don't have to use this hint, but that way you can do it as a product rule when you're taking the derivative there. You may, some people choose to think of it this way. All right, but I do think you'll find it easier if you do it this way. So just think of the square root of x times y times x to the 1/2 times y to the 1/2, and I think that the work that you do will be a little easier if you do it that way. Okay, that's it for this lecture, and I will talk to you next video.